Before July 2025, interstellar visitors were curiosities, not threats. Oumuamua and Borisov had already rewritten textbooks, but both eventually slid back into the comfort of natural explanations. Then came 3I Atlas brighter, faster, chemically stranger. What if this one isn't just a cosmic rock? What if, buried beneath the coma of dust and ice, lies intention? Tonight, we're going to explore that question carefully, calmly, one chapter at a time. Always with the science, but never afraid to wander into speculation. Settle in, slow your breathing, and let's wonder together. What if 3I Atlas is alien? On the night of July 1st, 2025, a faint speck of light appeared on the digital feed of the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS. Based in Chile, this robotic survey telescope had been built for vigilance, designed to detect small asteroids that might one day pose a threat to Earth. Every 30 seconds, its cameras swept across the southern sky, capturing the slow dance of stars, the faint smudges of galaxies, and the occasional movement of a near-Earth object. Most of the time, these automated scans revealed nothing unusual. But on this night, the algorithms flagged something strange, a point of light moving just a little too fast. At first, it seemed unremarkable. Telescopes flag fast-moving objects all the time, and usually they turn out to be small asteroids making their routine journey through the inner solar system. But within hours, astronomers began to realize that this object was different. Its motion didn't fit the usual patterns. The calculated orbit was not elliptical, not bound by the sun's gravity at all. Instead, the numbers revealed a hyperbolic trajectory, the mathematical signature of an interstellar visitor. By morning, word had spread to observatories across the globe. Confirmation came quickly from Pan-STARRS in Hawaii and the Zwicky Transient Facility in California. 3 independent observatories, separated by oceans, had detected the same impossible traveler. This was no asteroid from the belt, no long-period comet falling in from the Oort cloud. This object had come from the stars themselves. It was soon given a designation, 3I Atlas, the third confirmed interstellar object in human history. The discovery carried weight because of its predecessors. In 2017, Oumuamua stunned the world with its elongated shape and its strange acceleration, sparking fierce debates about whether it might have been artificial. Then, in 2019, 2I, Borisov showed up a more conventional interstellar comet, complete with a glowing coma and tail. 2 visitors, 2 very different personalities. And now, in 2025, a third, brighter, faster, stranger still. The first glimpse was just numbers on a screen, but those numbers hinted at a story far larger than themselves. Calculations showed 3I Atlas was racing inward at over 130, 0 miles per hour, nearly twice as fast as Borisov, and 5 times faster than Oumuamua. Even more intriguing was its timing. Its closest approach to Earth wouldn't bring it dangerously near at its closest. It would still be 270 million kilometers away, about twice the distance between Earth and Mars. It posed no threat. And yet, astronomers felt something else. Curiosity mixed with unease. Why was this object so fast? Why was it so bright, even at such great distances? As more telescopes locked onto it, the mysteries deepened. The Hubble Space Telescope captured a faint, glowing coma, proof that 3I Atlas was outgassing not just a rock, but a comet. The James Webb Space Telescope soon revealed chemistry unlike anything seen before, a coma dominated by carbon dioxide, with a CO2 to water ratio that defied every model of cometary formation. These were not the fingerprints of an ordinary traveler. For scientists, that first glimpse was both exhilarating and frustrating. Here was a messenger from another star, carrying with it the frozen chemistry of an alien nursery. Yet, it was moving so quickly, its time in our cosmic neighborhood would be brief. Only months to study, then gone forever, lost back into the void. But outside the observatories, speculation bloomed. If Oumuamua had raised questions about alien technology, what would people make of 3I Atlas? Was its strange chemistry just the legacy of a distant sun, or something designed to confuse? Was its hyperbolic trajectory simply the product of chance, or the deliberate navigation of something more? That first glimpse didn't answer these questions. It only posed them, quietly, against the background hum of the universe. A faint dot on a telescope's feed, a moving point of light among the stars. Yet, from that dot, an entire story unfolded, one that would stretch the limits of science, imagination, and human wonder. When astronomers first traced the trajectory of 3I Atlas, one number leapt off the page: its speed, over 130 miles per hour, or about 209 kilometers per hour. To put that in perspective, a bullet fired from a high-powered rifle leaves the barrel at around 500 miles per hour. The International Space Station orbits Earth at 17,500 miles per hour. Voyager 1, the most distant human-made object, coasts through interstellar space at just under 40 miles per hour. 3I Atlas was moving more than 3 times faster than Voyager, and yet it had reached us without slowing down, without showing any sign of fatigue from its billion-year journey. That kind of velocity isn't just fast, it's a message. In celestial mechanics, speed tells a story. The planets circle the sun in closed ellipses because they are bound, their velocities forever balanced against gravity's pull. Comets from the Oort cloud fall inward on long, stretched ellipses, only to return centuries later. But 3I Atlas, its path was hyperbolic. That means it wasn't bound at all. It came in, it would swing around the sun once, and then it would leave forever, slipping back into the darkness of interstellar space. For astronomers, this was reassuring. A hyperbolic orbit meant there was no danger of capture, no threat of collision with Earth or other planets. Its speed guaranteed a safe passage, but it also raised questions. Why so fast? Part of the answer lies in where 3I Atlas likely came from. Simulations suggest that interstellar objects are flung into the void during the chaotic youth of star systems. Giant planets, tugging and tossing debris, can accelerate comets to escape velocity, ejecting them into the galaxy. Over millions of years, those objects wander, carrying with them the chemistry of their birthplaces. By the time they cross another star system, they can be moving at extraordinary speeds. 3I Atlas may be one of these exiles, a survivor of gravitational violence, traveling light years as a frozen messenger. But here's where speculation enters. The first 2 interstellar visitors had been fast, but not this fast. Oumuamua's hyperbolic excess speed was about 26 kilometers per second. Borisov, 32 kilometers per second. 3I Atlas clocked in at around 61 kilometers per second, nearly double. Is that simply coincidence? A statistical roll of the cosmic dice? Or is it something more deliberate? Some astronomers have whispered that if an advanced civilization wanted to send probes between the stars, speed would be both a challenge and an advantage. Too slow, and a probe would take millions of years to arrive. Too fast, and the risk of collision with interstellar dust rises dramatically. But perhaps civilizations capable of engineering such journeys would aim for speeds just like this. Fast enough to cross between stars in reasonable time frames, slow enough to remain stable. Then there is the precision of the trajectory itself. 3I Atlas isn't wandering aimlessly. Its hyperbolic path threads through the solar system with geometry almost too neat, giving observers on Earth and Mars windows of opportunity to study it. Natural? Almost certainly. But some wonder if this is the signature of intention, a cosmic flyby planned not by chance, but by design. Of course, the mainstream explanation is simpler. Gravity is impartial, and chance encounters with giant planets in alien systems can sling objects to incredible velocities. In that sense, 3I Atlas isn't too fast at all. It's exactly as fast as physics allows. Still, when we compare it to its predecessors, the pattern feels uncanny. Each interstellar visitor faster than the last, each one stretching the limits of what we thought possible. Too fast or just right? The answer depends on perspective. To science, the speed of 3I Atlas is a natural consequence of ejection and time. To speculation, it is a tantalizing clue, an echo of precision that leaves room for wonder. As it streaks past our sun, the truth remains just out of reach, hidden in the silence between numbers, where fact and imagination meet. When astronomers pointed the James Webb Space Telescope at 3I Atlas on August 6, 2025, they expected to see something familiar. Most comets, whether from our own solar system or imagined from others, follow a fairly simple chemical script. As they warm in the sunlight, frozen water ice sublimates first, releasing vapor and dust to form a glowing coma. Then come other volatiles: carbon monoxide, carbon dioxide, and a handful of trace compounds. The ratios between them tell a story where the comet formed, what temperatures it endured, and how its chemistry evolved over billions of years. But 3I Atlas broke that script entirely. Webb's infrared instruments revealed a coma dominated not by water vapor, but by carbon dioxide. The ratio was startling: 8 parts carbon dioxide for every 1 part water. For comparison, most comets in our solar system are water-rich, with water to CO2 ratios closer to 10 to 1, or even 100 to 1. Here, the numbers were flipped upside down. That discovery sent ripples through the astronomical community. If 3I Atlas truly formed in another star system, then its composition should reflect the chemistry of that nursery. But what kind of planetary disk produces a comet with such an extreme preference for carbon dioxide over water? The possibilities challenge the models we've spent decades building. One natural explanation is that 3I Atlas was born near the carbon dioxide snowline of its parent star system. Just as water, methane, and ammonia freeze at different temperatures, carbon dioxide condenses at a unique threshold. If this comet formed in that narrow zone, it might have accreted more CO2 ice than water, locking in a chemistry unlike anything seen in our own system. Another theory is that billions of years of cosmic radiation altered its surface, breaking down water, ice, and leaving behind crusts rich in carbon dioxide. A third scenario involves layers of insulating dust. Over time, such a mantle could trap water deeper inside while allowing carbon dioxide to escape, giving the appearance of a CO2-dominated comet, even if water still lurks below. All three explanations fit within physics, and yet none feel completely satisfying. Why does this object release such extraordinary amounts of carbon dioxide, even when far from the sun, at distances where most comets are still dormant? Why does its coma extend hundreds of thousands of kilometers, larger than the Earth-Moon system, with activity levels that seem almost industrial in scale? It is here that speculation takes root. What if this chemical anomaly is not just the fingerprint of alien formation, but something more deliberate? Some have imagined the coma as a kind of exhaust, the byproduct of internal systems awakening as sunlight warms hidden machinery. Others wonder if the ratios themselves could be a form of code, molecular signatures arranged not by chance, but as a message written in chemistry. The idea may sound far-fetched, but history urges caution. In 1967, when Jocelyn Bell Burnell first detected the regular pulses of what we now know as a neutron star, the signal was so precise Her team briefly labeled it LGM-1 for Little Green Men. They quickly discovered the natural explanation, but the lesson remains. Sometimes, the universe imitates intention with unsettling precision, even if 3I Atlas is entirely natural. Its chemistry forces us to revise our assumptions. It tells us that planetary nurseries across the galaxy are more varied than we once believed, producing comets with compositions that challenge our expectations. But if we allow ourselves a moment of wonder, we can also imagine that perhaps these anomalies are more than quirks of physics. Perhaps they are signatures subtle, patient, and left for us to find only when our instruments became sharp enough to notice. For now, the simplest answer remains the most likely. 3I Atlas is a comet shaped by conditions unlike those of our solar system. And yet, as its carbon dioxide breath continues to fill the void, expanding into a ghostly sphere that dwarfs planets, we cannot help but ask, what story is it really telling? A story of alien chemistry, or of alien intention? Every celestial object has a rhythm, a way of catching and reflecting light as it tumbles through space. Astronomers call this a light curve, a simple graph of brightness over time. For asteroids and comets, light curves are like fingerprints. They reveal rotation rates, surface shapes, and sometimes even hidden companions. A tumbling rock will brighten as one side turns toward us and dim as it rotates away, producing a repeating pattern as steady as a heartbeat. So when scientists turned their instruments toward 3I Atlas and began mapping its light curve, they expected something familiar. They did not get it. Instead of chaotic variations or messy brightness spikes, 3I Atlas displayed a strangely stable rhythm. Its brightness waxed and waned in a near-perfect cycle of about 7.3 hours. But layered within that main beat were subtler oscillations, secondary variations that suggested a geometry far more complex than a simple spinning comet. For weeks, astronomers tracked this rhythm. Normally, small bodies in space show irregularities. Impacts and gravitational tugs leave asteroids wobbling. Sublimating jets of gas push comets into unpredictable spins. Even Oumuamua, our first interstellar visitor, showed a light curve so elongated it hinted at a cigar-shaped body tumbling chaotically. But 3I Atlas seemed different. Its cycles were consistent, steady, almost mechanical. Natural explanations exist. Perhaps the nucleus of 3I Atlas has a balanced, symmetrical shape. If so, its rotation might appear unusually stable compared to the jagged rocks we know. Or maybe we are simply viewing it from a lucky angle, one that masks the true irregularities of its spin. Still, the data left astronomers uneasy. It was almost too clean. Speculation grew. If an advanced object wanted to mimic the behavior of a comet while still maintaining control, what would its light curve look like? Some suggested that the steadiness might hint at active orientation control, like a spacecraft adjusting its attitude with precision, rather than leaving it to chance. Others wondered if the secondary oscillations reflected surface features that weren't random craters or boulders, but engineered panels or structures catching sunlight in predictable ways. Supporting that suspicion were radar echoes from Goldstone's deep space antenna. Instead of the rough scatter typical of natural bodies, 3I Atlas sometimes produced specular, mirror-like reflections, as though parts of its surface were smooth and angled. Combine those reflections with the strangely stable light curve, and a picture emerges that is at least worth questioning. Are we watching a comet spin, or something designed to look like one? Of course, science urges restraint. Comets can be tricky. Their outgassing can stabilize a spin rather than destabilize it. Jets of gas might vent in such a way that the rotation remains constant, like tiny thrusters keeping balance. Symmetry in surface composition can also mask expected variations, producing smoother brightness changes. In other words, The universe doesn't need to be artificial to appear intentional. And yet, the human mind can't help but wonder. When the light curve of 3I Atlas is plotted on a screen, the lines and oscillations look eerily regular, like signals waiting to be decoded. They remind us that sometimes nature hides its secrets behind patterns that resemble messages. The pulsars first labeled LGM-1, or the mysterious WOW, signal of 1,977. Both seemed like calls from intelligence until science revealed otherwise. But before those revelations, for a moment, they carried the weight of possibility. 3I Atlas carries that same weight now. Perhaps it is just an unusually stable comet, its nucleus shaped by chance into something smooth and consistent. Or perhaps, hidden beneath its dusty veil, it is something more, a probe, a relic, or even a messenger, choosing to reveal itself only through subtle patterns of reflected light. For astronomers, the challenge remains the same: measure, compare, test, and seek natural explanations first. For the rest of us, gazing at the graphs from afar, it is enough to let the question linger. Why does this visitor's rhythm feel so deliberate? A cosmic accident or a cosmic signal? The truth remains hidden in the flicker of distant light, a mirror in the dark, radar echoes that shine. When astronomers study small bodies in the solar system, they often turn to radar. Unlike visible light, which can be scattered and blurred by dust and distance, radar beams penetrate darkness and return with information about shape, surface texture, and reflectivity. For decades, the giant dishes at Goldstone in California and Arecibo in Puerto Rico painted portraits of asteroids and comets by bouncing radio waves off their surfaces. The echoes told us whether those objects were rough or smooth, solid or fractured, spinning or tumbling. So when 3I Atlas appeared on the scene in July 2025, radar astronomers wasted no time. The 70-meter antenna at Goldstone was directed toward the newcomer, transmitting powerful pulses at 856 gigahertz, the same frequency used to map Venus and track near-Earth asteroids. What came back was strange. Typically, radar echoes from natural bodies scatter like light reflecting off sandpaper. Irregular rocks return diffuse, noisy signals that spread across frequencies. But the echoes from 3I Atlas were not diffuse at all. At certain rotation angles, they became sharp, specular, like a flash from a mirror in the dark. Flat surfaces seemed to be catching the radar beam and sending it straight back toward Earth. For days, the team checked their instruments, ruling out interference, testing calibration. But the pattern persisted. Most of the time, the radar behaved as expected, giving the fuzzy returns of an active comet. And yet, layered within that fuzz were flashes of precision, brief moments when the echoes looked engineered. Natural explanations exist. Ice can fracture into planes that reflect like glass. Some comets contain crystalline structures that behave like tiny mirrors when struck by microwaves. Even large boulders aligned in the right way could mimic smooth surfaces. But the reflections from 3I Atlas seemed unusually strong and unusually consistent, as though something more ordered was hiding beneath the veil of dust and gas. Speculation followed quickly. Could these mirror-like echoes be panels? Could they be evidence of metallic plating or structures aligned with intention rather than chance? If so, what purpose would they serve? Perhaps heat management, redirecting solar energy. Perhaps communications, bouncing signals in directions we cannot yet follow. Or perhaps nothing more than coincidence, amplified by our desire to find meaning in noise. Radar astronomy is humbling in its ambiguity. The echoes rarely give crisp images. Instead, they produce patterns of brightness and delay that scientists must reconstruct into models. With 3I Atlas racing past at over 130 miles per hour, the observation window was limited, and the data, though intriguing, could not prove anything beyond doubt. The mirror flashes might be significant, or they might not. Still, for those who saw the plots emerge on their screens, there was a sense of unease. Space is full of rocks. It is not full of mirrors. And if something reflects radar like polished metal, then the simplest explanations start to feel less certain. History offers parallels. In 1967, pulsars were first dismissed as too regular to be natural. In the 1970s, mysterious radio bursts were considered possible signs of intelligence until plasma physics revealed their origins. Nature, it seems, often surprises us with phenomena that masquerade as intention. But the opposite possibility remains. If intelligence exists beyond Earth, it might also choose to hide in the natural. What better camouflage than a comet, trailing dust and gas, indistinguishable from billions of others except for the occasional glint, a mirror in the dark. For now, the radar story of 3I Atlas remains unresolved. Scientists will catalog the echoes, compare them to known cometary behaviors, and likely file them under unusual but explainable. Yet the question lingers. Were we glimpsing natural fractures shaped by alien chemistry, or something deliberately built to shine only when noticed? In the silence of deep space, radar beams faded, their echoes trailing back across millions of kilometers. And in those echoes lay a riddle faint, fleeting, but unforgettable. A whisper in radio light that seemed to say, "Look closer." Every civilization that learns radio inevitably stumbles across one frequency above all others, the hydrogen line. It sits at exactly 420.4 megahertz, a whisper emitted when the most common element in the universe, hydrogen, undergoes a tiny flip in the orientation of its electron. Invisible to the eye, but bright to any radio antenna, this frequency is the universe's calling card. Hydrogen is everywhere. It makes up 3/4 of all normal matter, fusing in the cores of stars, drifting in the cold between galaxies, swirling in nebulae that birth planets. When its atoms flip from one quantum state to another, they release a photon of radio energy. Weak individually, but overwhelming in number, these signals fill the cosmos with a constant, gentle glow. Astronomers use the hydrogen line to map the spiral arms of our galaxy, to trace the rotation of the Milky Way itself, and to study the distribution of matter across the universe. It is, in many ways, the baseline heartbeat of creation. But for scientists who dream of contact, the hydrogen line has another meaning. In 1959, physicists Giuseppe Cocconi and Philip Morrison argued that any advanced civilization would know this frequency. Hydrogen is universal, and so is its spectral line. If you wanted to broadcast a message across the stars not in human language, but in nature's own, you would choose one, 420 megahertz. It is the cosmic equivalent of hanging a sign on the busiest highway. That is why the search for extraterrestrial intelligence, or SETI, has always favored this band. Decades of radio telescopes from Arecibo to Green Bank, from the Allen Telescope Array to FAST in China, have all listened there, scanning for narrowband signals that would stand out against hydrogen's natural hum. If aliens ever wanted to say, "We are here," the logic goes, they would place their call where all astronomers are already listening. And so, when 3I Atlas entered our solar system, and faint reports emerged of a narrowband tone near the hydrogen line, drifting with its motion, ears perked. At first, the idea was dismissed as interference, a stray transmission from satellites, or noise from Earth's crowded spectrum. But multiple observatories reported the same thing. The Very Large Array in New Mexico, the Green Bank Telescope in West Virginia, and FAST in China all recorded it. The signal appeared only when antennas were pointed directly at 3I Atlas. It Doppler shifted in perfect synchrony with the object's trajectory. It was faint, yes, but coherent, precise, and astonishingly stable. Could this be natural? Comets are known to emit radio noise as sunlight interacts with their gas and plasma tails. Yet those emissions tend to be broad, messy, and chaotic. They do not produce the razor-thin tones that hug a single frequency like a violin string held perfectly in tune. And why, of all places in the spectrum, would the emission sit right next to hydrogen's universal line? Coincidence is possible, but uncomfortable. For scientists, the discipline is clear. Extraordinary claims require extraordinary evidence. A few nights of correlation do not make a discovery. Interference must be ruled out. Alternative natural processes must be explored. Plasma instabilities, magnetic turbulence, even exotic chemistry, all could, in theory, mimic a narrowband signal. The cautious conclusion is always the same. Wait for repeatability. Test against background. Never leap to aliens. And yet, in the quiet hours, one cannot help but reflect. If you were going to design a probe to be noticed, where would you whisper? You would hide in plain sight, inside the one frequency every civilization capable of radio astronomy knows, the hydrogen line. For now, the tone near 420 MHz remains an anomaly, a puzzle still under investigation. Perhaps, with time, data will reveal a natural explanation. Perhaps the signal will fade, forgotten among thousands of false alarms, or perhaps, years from now, historians will look back and say, the first time we knew we were not alone was when 3I-ATLAS hummed to us in hydrogen's voice. Long before 3I Atlas appeared in our skies, humanity had already been sending signals into the dark, not on purpose at first, not with careful planning or deliberate intent, but simply as a side effect of becoming a technological species. Every radio broadcast, every television transmission, every radar ping has been leaking into the void for more than a century. Together, they form what scientists call the radio bubble, an expanding sphere of electromagnetic noise centered on Earth, now more than 100 light-years across. Imagine it. A cosmic balloon, invisible yet real, stretching outward at the speed of light. Inside that bubble is the entire history of our electronic age. The first scratchy Morse code signals, the crackling voices of early broadcasters, the sounds of baseball games, presidential speeches, and orchestras playing through static. Later came television dramas, news reports, sitcoms, and commercials, all climbing the invisible ladder of the atmosphere and streaming outward forever. Every second that passes, the bubble grows larger, another light second across, announcing to the galaxy that something is alive and speaking here. To us, it feels ordinary. But to anyone listening from the outside, the bubble would stand out against the quiet hum of the galaxy. Earth shines in radio like a lighthouse in fog. Most of our signals, weak and scattered, fade into the background after a few light years. But some transmissions, powerful planetary radars, military over-the-horizon systems, the deep space network talking to spacecraft, are strong enough to be detectable across interstellar distances. These beams sweep across the cosmos like searchlights, narrow but intense, impossible to miss if you happen to be in their path, which leads to an unsettling thought. We have not been quiet. For 123 years, we have been shouting into the dark without meaning to. And in 1974, we shouted deliberately. The Arecibo telescope, then the most powerful radio dish in the world, sent a tightly packed message toward the star cluster, M13. A simple pictogram of humanity numbers, DNA, a sketch of our solar system. It was ceremonial, never expected to be answered. M13 is 25, 0 light-years away. But what if someone closer was already listening? This is where 3I Atlas enters the story. The hydrogen line whispers near its trajectory made some wonder. Could this visitor be connected to our transmissions? If our radio bubble has reached more than 100 nearby stars, could a civilization orbiting one of them have heard us and sent something in reply? A messenger disguised as a comet, a probe hidden in plain sight. Mainstream science leans toward caution. There is no hard evidence linking 3I Atlas to Earth's accidental broadcasts. Its path, while intriguing, is consistent with natural ejection from a distant planetary system. Its chemistry, though unusual, does not prove intent. And yet, the coincidence is difficult to ignore. Only decades after our strongest transmissions began lighting up the sky, interstellar visitors began appearing with greater frequency. First Oumuamua, then Borisov, and now Atlas, each stranger than the last. The thought lingers. What if the radio bubble is not just noise, but a beacon? What if we have already been heard? For all of human history, we have wondered what might happen if we called into the dark. But perhaps the truth is that we have been calling all along, unintentionally. With every sitcom laugh track and every radar sweep, if 3I Atlas is natural, then its presence is a reminder of how small we are. How many billions of wanderers must crisscross the galaxy at any given time. But if there is any connection, even the smallest hint, between our accidental broadcasts and its sudden arrival, then the implications are profound. It would mean we are no longer the only storytellers, that someone, somewhere, has been listening to the radio bubble and decided to answer. For now, the bubble keeps growing, expanding another light second with every passing heartbeat. Out there, our first hellos are still traveling, carrying the songs, the speeches, the arguments, and the laughter of a young civilization into the endless night. Whether 3I Atlas is coincidence or reply, the message is the same. Earth has spoken. On November 16th, 1974, the Arecibo Observatory in Puerto Rico became, for a brief moment, the brightest radio source in our corner of the galaxy. Its giant 305-meter dish, normally used to map asteroids and study pulsars, turned its gaze toward a globular star cluster known as M13, some 25 light-years away. From that vast distance, no reply could ever be expected. Yet the transmission itself was symbolic, a deliberate declaration that humanity was here, aware, and ready to say hello. The message contained exactly 679 bits of information, chosen because 679 is the product of two prime numbers, 23 and 73. Any recipient with even basic mathematical knowledge could arrange the bits into a rectangular grid and see the picture it formed. There, pixelated but clear, were patterns. Our numbers 1 through 10, the chemical bases of DNA, a sketch of the double helix, a stick figure human, our solar system with Earth marked, and the outline of the Arecibo dish itself. It lasted only 3 minutes, powered by a megawatt of radio energy, but it was a shout into the void unlike anything before it. Most scientists knew the odds. By the time the message arrives at M13, Earth's continents will have shifted, human civilizations will have risen and fallen, and languages may have changed beyond recognition. But the point wasn't to start a conversation. The point was to prove that we could. Carl Sagan called it a bottle tossed into a cosmic ocean, a note written more for ourselves than for the distant stars. And yet, the timing is what unsettles some today. Only a few decades after Arecibo's deliberate call, interstellar visitors began arriving. First Oumuamua in 2017, then Borisov in 2019, and now 3I Atlas in 2025, bigger, faster, stranger still. To a cautious scientist, this is coincidence. Space is vast, filled with debris ejected from newborn star systems. The fact that we are finally noticing these wanderers says more about our improved telescopes than about cosmic intent. But to a speculative mind, the overlap invites questions. What if we were heard, not by Mem-13, but by someone closer? After all, our accidental radio bubble has already washed over more than 100 nearby stars. The Arecibo transmission may have been ceremonial, but it symbolized a shift. Humanity's first deliberate step into the interstellar conversation. What if someone saw that step and decided to respond, not with words, but with presence? Imagine being an advanced civilization, listening to the radio noise of the galaxy. Most worlds are silent, but one small blue planet suddenly lights up with chatter. Music, television, radar sweeps, and then a sharp intentional burst aimed at the stars. Would that not draw attention? And if you had the technology to send probes disguised as comets, would you not send one? Something that could pass unremarked by most, but reveal itself to any civilization curious enough to look closer. 3I Atlas, with its hyperbolic path, its carbon dioxide coma, and its radar flashes, becomes part of this speculation. It is not proof, but it is coincidence layered upon coincidence. A ceremonial message sent half a century ago, a radio bubble spreading invisibly into the void. And then, visitors arriving, carrying mysteries we struggle to explain. The scientific consensus remains firm. 3I Atlas is most likely natural, a cometary fragment from an alien nursery. But the timing whispers otherwise. It tempts us to wonder whether our first cosmic greeting card has already been answered not with words in hydrogen, but with a physical messenger drifting past our sun to remind us that the universe may be listening more closely than we think. And so the Arecibo message, once seen as a gesture of hope, now feels like a seed. Whether it grows into conversation, contact, or only coincidence remains unknown. But its echo lingers in every new discovery, and with 3I Atlas glowing in our skies, we cannot help but ask, did we summon this? For over a century, humanity has been whispering into the cosmos without meaning to. Our earliest radio experiments leaked into space, scattering fragments of speech, music, and static into the void. Over time, those whispers grew louder. Television broadcasts, military radars, deep space communication arrays. Together, they formed a bubble of electromagnetic noise now stretching more than 100 light-years in radius, brushing against nearby stars we have never seen with the naked eye. Then, in 1974, came the Arecibo message, deliberate, focused, a true attempt at saying hello. A handful of minutes, a burst of raw power, encoding our DNA, our numbers, our place in the solar system. It was meant as a gesture, symbolic more than practical. M13, the cluster it was aimed at, is too far for a reply to ever return in human lifetimes. But the act itself mattered. It was humanity declaring, for the first time, that it was ready to join a conversation. Now, 51 years later, a question lingers like a shadow. Could 3I Atlas be the reply? At first glance, the thought seems fanciful. The comet's discovery on July 1st, 2025, was a triumph of astronomy, not of messaging. Its orbit is hyperbolic, its chemistry unusual but explainable, its path predictable. Astronomers are careful to insist. This is most likely a natural fragment, ejected from some distant star system long before Earth was even formed. It cannot be sent in the way we imagine sending spacecraft. It is older than us, older than our civilizations, older perhaps than our entire solar system, and yet, the coincidences pile up. Its speed is higher than that of Oumuamua or Borisov, almost as if each interstellar visitor grows more remarkable than the last. Its coma, dominated by carbon dioxide instead of water, defies models of cometary chemistry, as if advertising its difference. Its radar echoes flash back with moments of strange clarity, like polished mirrors hidden in ice. And then there is the faint radio tone hovering near the hydrogen line, reported by multiple observatories, not proof, but a whisper, hard to ignore. Skeptics point out that nature is often stranger than we expect. Oumuamua's odd acceleration was eventually explained as outgassing. Borisov behaved more like a standard comet, but still reminded us that interstellar chemistry is diverse. 3I Atlas, they argue, simply continues this lesson. The galaxy is filled with wanderers, each one shaped by unique environments we have never sampled before. Coincidences, not replies. Physics, not intent. But for those willing to wonder, the narrative unfolds differently. What if our unintentional radio bubble was heard not by M13, but by someone much closer, a nearby star system within a few dozen light years? What if they decided to respond, not with a beam of radio, but with a physical probe? Something disguised as natural debris, something that could drift undetected until our instruments were advanced enough to notice its oddities. A visitor, hidden in plain sight, wearing the mask of a comet. It sounds like science fiction, and yet history warns against quick dismissal. Pulsars were once called little green men. The WOW, signal of 1977, still defies complete explanation. Fast radio bursts, once a puzzle, turned out to be magnetars, proof that nature can mimic intention. But what if, this time, intention is real? If 3I Atlas is a reply, it is not a simple one. It carries no obvious message, no blinking lights or engraved plaques. Instead, it confronts us with mystery, chemistry that doesn't fit, light curves that don't add up, echoes that shine like mirrors in the dark. Its presence forces us to ask questions about what we know and what we assume. Perhaps the reply isn't words at all. Perhaps the reply is simply the visitor itself. Whether coincidence or communication, 3I Atlas reminds us of something profound. We are no longer just observers of the cosmos. We are participants. We have spoken into the dark, and now something has come near enough to make us wonder if the dark has answered back. When we look at the night sky, comets seem like nothing more than icy wanderers, dirty snowballs drifting along paths carved by gravity and time. They are among the most ancient objects in our solar system, relics of its earliest days. Their tails, streaming in the sunlight, have inspired both fear and wonder for millennia. But what if some comets are not what they appear to be? What if, hidden among the countless natural bodies that pass through our skies, there are watchers? Silent, patient, disguised in dust and ice, the idea is not new. In 1960, British astronomer Ronald Bracewell speculated that advanced civilizations might send robotic probes across the galaxy, designed to observe quietly rather than announce themselves with radio beacons. These Bracewell probes, he argued, would be far more efficient than shouting across light years of distance. Instead of waiting for signals, civilizations could learn by listening, by watching, by embedding their technology in places where it would be mistaken for something ordinary. And what better disguise than a comet? Comets are expected to appear, expected to behave strangely, expected to drift in and out of our skies without lingering too long. They are perfect camouflage. Dust clouds hide surfaces. Outgassing masks anomalies. Radar reflections scatter into noise. A probe encased in ice could remain undetected for eons, activating only when warmed by a nearby star. 3I Atlas, with its mirror-like radar echoes and carbon dioxide overdrive, naturally invites such speculation. Its chemistry is not what models predict. Its light curve seems oddly stable. Its speed places it on a path through our solar system that feels almost too convenient, giving us just enough time to study it before it vanishes. Could this be coincidence? Almost certainly. But if one were designing a surveillance asset meant to appear natural, these are exactly the traits one might expect. Science, of course, demands caution. There is no evidence that 3I Atlas is artificial. Every anomaly has possible natural explanations. Fractured ice, reflecting radar, dust mantles altering chemistry, symmetrical geometry producing stable rotations. And yet, the possibility of silent watchers persists in the imagination because it solves a puzzle known as the Fermi paradox. If intelligent civilizations exist, why don't we see them? One answer is simple: because they are not broadcasting. They are watching. Imagine probes seeded through the galaxy, each one indistinguishable from a comet, each one silently gathering data. When a young civilization like ours begins to broadcast into space, these watchers drift closer, drawn not by chance but by design. They do not interfere, they do not land, they do not reveal themselves. They only observe, cataloging our technology, our behavior, our readiness. To us, they look like harmless wanderers. To them, we are the subjects of a very long experiment. It is a haunting thought, not hostile, not catastrophic, but unsettling in its subtlety. Surveillance disguised as nature, an intelligence so advanced that hiding inside the ordinary is trivial. We scan the skies for threats, for incoming rocks, for bright collisions. But what if the real visitors are already here, blending into the very background of our astronomy? For now, 3I Atlas remains a comet in the official record, natural, fast, fascinating, but harmless. Still, as we look at its tail stretching through the blackness, it is hard not to wonder. What if some comets are not just relics of creation, but instruments of observation? What if their silence is not emptiness, but intent? Perhaps we will never know. Or perhaps, centuries from now, when our own probes wander into other star systems, we will use the same disguises. Dust and ice, tails and comas, hiding in plain sight the perfect masks for watchers who never wish to be seen. The solar system is a clockwork machine. Planets, moons, asteroids, and comets all move according to the same laws. Gravity, momentum, the geometry of Kepler's ellipses. Over centuries, astronomers have grown accustomed to the elegance of these motions. A comet swings in from the Oort cloud, traces a long curve around the Sun, and drifts back out again. An asteroid tumbles along a stable orbit between Mars and Jupiter. The patterns are predictable, orderly, almost reassuring. But then came 3I Atlas. From the first calculations, its path stood out. Hyperbolic, yes, unbound, destined never to return. That alone was not surprising. Both Oumuamua and Borisov had shown the same trait. What troubled astronomers was the precision of its trajectory. 3I Atlas threaded the solar system with uncanny neatness, weaving between planetary orbits as if choosing visibility, skirting just close enough to invite observation but never close enough to risk collision. On October 3, 2025, for instance, it would pass within 29 million kilometers of Mars, closer than some of Mars's own spacecraft. For the fleet of orbiters circling the red planet, this presented a once-in-a-lifetime chance to capture detailed images. Weeks later, its perihelion would place it at a distance of 130 million miles from the Sun, hot enough to trigger activity, but not so close as to destroy it. Then, when Earth was on the far side of the Sun and unable to observe, 3I Atlas conveniently slipped behind the glare, re-emerging in December in the pre-dawn skies for a final round of study. It was almost theatrical, as if the timing had been choreographed for maximum intrigue. Most astronomers insist this is coincidence. Orbital mechanics can produce alignments that appear intentional when viewed from one perspective. Given enough wanderers, some will pass through in ways that look convenient for us. Yet, in the silence of the observatories, a question lingered. Why does this particular visitor give us just the right windows, just the right geometry, just enough time to notice? Some compared it to Oumuamua's trajectory. That earlier interstellar object seemed to accelerate slightly as it left the solar system, a motion first explained only by hypothesizing hidden outgassing. The explanation fit the data, but many found it unsatisfying. Was it outgassing, or was it something more deliberate? With 3I Atlas, the suspicion grew stronger. Its path was clean, almost mathematical, as though it had been plotted rather than stumbled into. Speculative thinkers go further. They suggest that if an advanced civilization wanted its probe to be noticed, but not too noticed, this is exactly the kind of trajectory it might choose. Close enough for telescopes to study, far enough to avoid panic. Timed so that multiple observatories, including those at Mars, would have a chance to observe. A cosmic flyby presented like an invitation. Of course, the laws of physics remain firm. Gravity shapes every path, and chance is a powerful sculptor. To believe in intention is to risk falling into the same trap that once labeled pulsars as little green men. Yet it is also true that orbital mechanics can be exploited. Just as we use gravity assists to sling our spacecraft toward distant planets, so too could someone else. If 3I Atlas is a probe, then perhaps its perfect threading of the solar system is no accident at all, but the result of careful planning ages ago. For now, the consensus is simple. Its orbit is natural, remarkable only because it is rare. But for those who look at its geometry and feel the tug of unease, the thought persists. Perhaps the perfection of its path is the message itself. Not words, not signals, but choreography. A silent dance across our sky, hinting at a mind behind the motion. Gravity is the great governor of motion in the universe. Every rock, every planet, every star bends space in proportion to its mass, pulling everything around it into predictable curves. When astronomers trace the paths of comets, they rely on gravity's reliability. The sun pulls, the comet follows, and the orbit can be plotted with exquisite precision. But sometimes, comets don't obey. Even in our own solar system, comets often experience what scientists call non-gravitational accelerations. These small but measurable changes happen because comets are not inert rocks. They are fragile bodies of ice and dust. As sunlight heats their surfaces, ices sublimate, jetting gas into space. Each puff acts like a miniature thruster, nudging the comet in ways that gravity alone cannot explain. Most of the time, these nudges are irregular, unpredictable, and small. But with sensitive enough instruments, they become obvious, adding quirks to otherwise smooth orbits. Oumuamua, the first interstellar visitor, displayed exactly such a quirk. As it left the solar system in 2017, astronomers noticed it was accelerating slightly more than expected. At first, the explanation was outgassing, though no coma or tail was visible. Some argued this meant Oumuamua might not be a comet at all, but something stranger, even artificial. The debate still lingers today. Now, with 3I Atlas, the question arises again. As telescopes tracked its motion across the sky, subtle deviations appeared. The trajectory, while largely consistent with gravity's pull, included small accelerations that could not be explained by mass alone. The first interpretation was straightforward: outgassing. After all, 3I Atlas has a massive carbon dioxide coma, a sphere of gas large enough to envelop the Earth-Moon system. Such activity would naturally produce jets, and jets would naturally produce nudges, but the details are troubling. The acceleration seemed unusually smooth, almost continuous, rather than chaotic bursts. With most comets, outgassing produces irregular flickers, depending on which surface region faces the sunday. 3I Atlas, however, showed a kind of steadiness, a persistent push in directions that looked more like calculated thrust than random venting. Is this simply a matter of perspective? Perhaps the geometry of the nucleus hides the irregularities from our view. Or perhaps its rotation aligns its jets in such a way that they cancel out noise, producing the illusion of smoothness. These are plausible explanations, and many astronomers are satisfied with them. Yet the speculation cannot be silenced. What if the nudges are not natural? What if they are engines, subtle but intentional, guiding the object along a chosen path? A civilization capable of sending a probe across interstellar space would need propulsion, and outgassing, if controlled, could serve as camouflage. A ship that vents gases deliberately could mimic a comet perfectly, hiding in plain sight. The very ambiguity is what fuels the intrigue. To the instruments, a jet of carbon dioxide and a thruster plume might look the same. Both produce acceleration, both alter orbits, both leave signatures difficult to distinguish at millions of kilometers. To us, they are nearly indistinguishable. To an advanced intelligence, that ambiguity could be the point. Still, science demands restraint. The consensus remains that 3I Atlas is natural. Its nudges the product of unusual but explainable cometary activity. Yet, in the margins of the data, a thought persists. Perhaps the difference between outgassing and engines is not what we see, but what we assume. One interpretation reassures us that the universe is predictable. The other suggests that it is not. As 3I Atlas continues its passage, every shift in its orbit is measured with care, every deviation plotted against models of sublimation and solar heating. Each time the numbers line up, scientists breathe easier. But each time they do not, imagination stirs. Outgassing or engines? The answer may forever remain hidden within the veil of dust and gas. For now, we are left with the humbling reminder that not everything in the sky can be explained with certainty, and that sometimes the smallest nudges carry the greatest mysteries. On the night of August 15th, 1977, a radio telescope in Ohio heard something it had never heard before. The Big Ear Observatory, run by Ohio State University, was quietly scanning the skies as part of the SETI project, the search for extraterrestrial intelligence. Its instruments recorded streams of data on long sheets of paper, numbers and letters representing the strength of radio signals across the spectrum. Most of it was ordinary. Background noise, static, the hiss of the galaxy. But then, for exactly 72 seconds, the numbers spiked. The signal was so strong, so clean, and so narrow in frequency that the astronomer on duty, Jerry Eman, circled it in red ink and wrote one word in the margin: "Wow." That annotation gave the signal its name, and it has haunted astronomy ever since. The wow signal came from near the constellation Sagittarius, close to the center of our galaxy. It appeared precisely at 1,420 megahertz, the hydrogen line, the same frequency many scientists had predicted would be the natural choice for an interstellar beacon. It was narrowband, unlike the broad smears of natural emissions, and it matched the characteristics of an intentional transmission. Yet it was fleeting. When telescopes turned back to the same patch of sky, nothing was there. In the decades since, no one has ever detected it again. For years, scientists have searched for explanations. Some proposed that it was a natural burst of hydrogen amplified by interstellar plasma. Others suggested interference from satellites or military signals bouncing off space debris. More recently, one theory argued that it might have been radio emissions reflected from a passing comet, though this explanation remains controversial, as no comet known at the time passed through that exact region. And so, the WOW signal remains an unsolved mystery. A momentary spike in the noise, possibly natural, possibly accidental, possibly something more. Now, with the arrival of 3I Atlas, the story takes on new resonance. In 2025, observatories listening near the hydrogen line reported faint, narrow tones that seemed to follow the object's trajectory. They were weaker than the wow signal, barely above the noise, but they were coherent, consistent, and persistent. Unlike the 1,977 detection, these whispers did not vanish immediately. They lingered for nights at a time, shifting exactly as Doppler calculations predicted they should if the source were moving with the comet. Could this be related? Could 3I Atlas, drifting through our solar system, carry with it the echo of what Jerry Eman scribbled nearly 50 years ago? Perhaps not directly the wow. Signal's origin remains uncertain, and the hydrogen line is crowded with natural emissions. But the parallels are enough to stir the imagination. Both events revolve around the same frequency, the same cosmic fingerprint. Both hint at something deliberate. Both leave us with data that is just clear enough to intrigue, yet not definitive enough to prove. The cautious view is that this is coincidence. Radio astronomy is messy. The universe hums with countless sources of noise, and our own planet adds layers of interference. Even the best instruments struggle to filter signal from static. The wow signal, scientists remind us, was likely a natural phenomenon or a reflection of human technology. The tones near 3I Atlas could be the same: plasma instabilities, chemical emissions, or overlooked interference. But to the speculative mind, the timing is poetic. The wow signal in 1977, the Arecibo message in 1974, and now, in 2025, a visitor streaking through the solar system, trailing whispers near the hydrogen line. A pattern emerges fragile, suggestive, but impossible to ignore. What if the wow signal was the first hello, and 3I Atlas is the follow-up? What if the conversation has been unfolding for decades, too slow and subtle for us to notice until now? Perhaps the truth is simpler. The wow signal was a mystery of its time, and 3I Atlas is a mystery of ours. Both remind us of the same lesson, that the universe still holds surprises, and that even in the vast silence of space, there are moments when the static sharpens into something that feels like a voice. In the winter of 1967, a young graduate student named Jocelyn Bell sat among rolls of chart paper, carefully inspecting the jagged lines produced by a new radio telescope in Cambridge. For weeks, she had been looking for quasars, distant, luminous galaxies. But instead, she found something unexpected. A signal that repeated every 3 seconds, sharp and regular, like a cosmic heartbeat. At first, no one knew what to make of it. Natural sources of radio waves tended to be messy, broad, and chaotic. This signal was precise, too precise. Jokingly, the researchers labeled it LGM-1 for Little Green Men. The idea, half serious, half skeptical, was that the pulse might be artificial, a beacon from an extraterrestrial civilization. Soon, more signals were found in other parts of the sky. They were equally regular, equally puzzling. It seemed unlikely that multiple alien transmitters would just happen to be discovered all at once. Slowly, a natural explanation emerged. These were pulsars, the collapsed remnants of massive stars, their magnetic fields beaming radio waves like cosmic lighthouses as they spun. The discovery earned a Nobel Prize and transformed astrophysics, but it also carried a humbling lesson sometimes. The universe produces patterns so orderly they appear intentional. This story matters when we think about 3I Atlas. The interstellar visitor has raised its own share of questions. The smoothness of its light curve, the mirror-like radar echoes, the whispers near the hydrogen line. Each of these traits invites speculation, tempting us to see intention where perhaps there is none. The pulsar story reminds us that nature, too, can mimic technology. Regularity does not always mean design. Precision does not always mean purpose. And yet, the other side of the lesson is just as important. When pulsars were first discovered, scientists did not dismiss the possibility of alien origin outright. They entertained it, tested it, and only when data ruled otherwise did they move on. That caution, balancing open-mindedness with discipline, is the mark of good science. It keeps us from leaping to conclusions, but also from closing doors too quickly. So, what does this mean for 3I Atlas? Perhaps its mysteries will one day resolve into natural explanations, just as pulsars did. Its carbon dioxide coma may reflect an unusual formation environment. Its radar flashes may come from fractured ice. Its non-gravitational nudges may be nothing more than outgassing, smoothed by geometry. In time, the anomalies may seem as ordinary as a spinning neutron star does today. But it is also possible that the lesson points in another direction. Pulsars taught us humility, but they also expanded our vision of what the universe is capable of. Before 1967, no one had imagined dead stars spinning so fast they could sweep radio beams across space like clockwork. The discovery reshaped astronomy. In the same way, 3I Atlas may reveal something we have not yet conceived. If not alien technology, then perhaps alien chemistry, alien geology, or alien dynamics that defy our current models. The danger lies in assuming too quickly and saying, "This is impossible," or "This must be aliens." The truth is usually somewhere between. The universe is neither ordinary nor miraculous. It is both, depending on how much we know at the time. For now, 3I Atlas remains an enigma, and we should hold it the way Jocelyn Bell once held her pulsar charts, with curiosity, patience, and respect. We may laugh at our early labels as we laughed at little green men, or we may find, decades later, that what looked like coincidence was something more. The lesson of pulsars is clear. Mystery is not weakness, it is the starting point of discovery. Whether 3I Atlas is comet, curiosity, or construct, it reminds us, as pulsars once did, that the universe still knows how to surprise us. In 2007, while combing through archived data from a radio telescope in Australia, astronomers stumbled across something astonishing. Buried in the noise was a pulse of radio energy unlike anything they had seen before. It lasted just a few milliseconds, yet in that brief instant it released as much energy as the sun emits in an entire day. This was the first fast radio burst, or FRB. At first, many assumed it was a mistake, a glitch in the instruments, a stray reflection from Earth. But then, more were found. Different telescopes, different skies, different times, all capturing flashes that shared the same signature, powerful, fleeting, and coming from far beyond our galaxy. Today, thousands of FRBs have been cataloged. Some occur only once, others repeat with eerie regularity. They arrive from every direction in the sky, as if the universe itself is peppered with these mysterious radio beacons. Most scientists now believe FRBs have natural origins. The leading candidate is the magnetar, a kind of neutron star with a magnetic field so strong it could erase the data on every credit card on Earth from halfway to the moon. When magnetars crack or flare, they can release bursts of energy powerful enough to light up the cosmos for milliseconds. Observations of young magnetars have indeed produced signals that resemble FRBs, lending weight to this theory. And yet, questions remain. Some FRBs repeat with clockwork precision, firing bursts every few days or weeks. Others show frequency structures, fine details within the signal that look almost like modulation. In 2019, One FRB was even detected with a 16-day cycle, a pattern that felt less like chaos and more like choreography. While natural explanations can be proposed binary star systems, orbital motions, or magnetars precessing like tops, the sense of intentionality is hard to ignore, which leads us to the speculation: could FRBs be artificial? If an advanced civilization wanted to signal across galaxies, short, bright bursts would be efficient. A millisecond flash could outshine an entire galaxy for that instant, easily detectable by radio telescopes like ours. Concentrated energy, repeated in patterns, could serve as beacons, lighthouses in the cosmic ocean. Some scientists have even calculated how a civilization might use FRBs to propel spacecraft with directed energy, pushing solar sails across interstellar distances. In this view, FRBs are not just messages, but tools, technological artifacts disguised as natural phenomena. Skeptics point out that extraordinary claims require extraordinary evidence. So far, no FRB has carried a clear message, no binary code, no mathematical sequence that shouts intelligence. The bursts are random, scattered, often distorted by their passage through intergalactic plasma. Every time one seems to hint at order, new data nudges it back toward the realm of astrophysics. The magnetar explanation, while not perfect, fits much of what we see, and yet the possibility lingers. Just as pulsars were once suspected to be alien signals before proving natural, FRBs could turn out to be entirely astrophysical. But unlike pulsars, which quickly revealed their true nature, FRBs remain elusive. We still do not fully understand them. And into that uncertainty, imagination rushes. Now consider 3I Atlas. As it streaks through our solar system, whispers near the hydrogen line have been reported, faint and narrowband. Could there be a link? Could FRBs and cometary visitors both be manifestations of a larger network? Natural phenomena harnessed by intelligence, or intelligence hiding within the natural? It is speculation, yes, but not beyond the realm of wonder. For now, the safest answer is that FRBs are natural, products of the most extreme stars the universe can produce. But their scale, their mystery, and their occasional hints of order remind us not to grow complacent. The line between nature and technology is thinner than we think, and history shows that the universe often surprises us with phenomena that masquerade as intention. Whether natural or not, FRBs remind us of possibility. They are proof that the cosmos still contains mysteries we cannot yet explain, and each burst, like 3I Atlas itself, is a whisper from the dark, urging us to listen more closely. When scientists look at comets, they see time capsules. These frozen bodies preserve the conditions of the star systems where they were born. By studying the gases and dust they release, we can reconstruct the temperatures, pressures, and chemical recipes of worlds light years away. A comet's coma, that ghostly cloud of vapor surrounding its core, is more than a spectacle. It is a message, written not in words, but in chemistry. With 3I Atlas, the message is unusual. Most comets in our solar system release water as their primary gas. Carbon dioxide and carbon monoxide appear too, but always in smaller amounts. Atlas, by contrast, seems to breathe carbon dioxide first and foremost, at levels 8 times greater than water. For astronomers, this ratio makes little sense. Water is abundant. It freezes at temperatures common in protoplanetary disks. Why would an interstellar comet suppress water while flaunting carbon dioxide? Several natural explanations have been offered. One is formation location. Perhaps Atlas was born near a carbon dioxide snowline, where temperatures favored CO2 over H2O. Another is radiation damage. Billions of years in interstellar space may have eroded its water ice, leaving behind carbon dioxide trapped in protected layers. A third is insulation, a dust crust that prevents water vapor from escaping, while CO2, stored nearer the surface, vents freely. Each of these theories is plausible. Each helps to reduce the puzzle, and yet the ratios remain extreme. This is where speculation takes hold. What if the chemistry is not an accident of nature, but a kind of code? Consider this. Any advanced civilization would know that astronomers study comets to understand planetary origins. If you wanted to signal intelligence without building giant radio beacons, you could alter the chemistry of a comet, make its ratios stand out, ensure that when it passes near another star, its emissions would scream anomaly. No advanced instruments would be needed, just the same telescopes already watching the skies. It may sound far-fetched, but history provides analogies. Humans have long hidden messages in unexpected places, knots in textiles, symbols carved into pottery, or ratios embedded in music. Chemistry could serve the same role on a cosmic scale. Ratios are universal. Numbers do not depend on language. If a comet exhibited proportions too strange to be natural, 8:1, 10:1, perhaps even a prime sequence, would that not be a message? Skeptics argue, of course, that nature already produces extremes. Oumuamua's acceleration seemed artificial until models suggested exotic outgassing. Borisov's chemistry was different from solar comets, but still natural. Atlas may simply be another reminder that our theories are incomplete. To leap to intelligence is to risk repeating mistakes, like when pulsars were jokingly labeled little green men. But there is a middle path. What if intelligence uses nature rather than replacing it? A probe disguised as a comet could alter its chemistry deliberately, masking itself while leaving a signature detectable only to curious astronomers. It would be camouflage and communication at once, silent observation, paired with a quiet, "We are here," hidden in the molecular fingerprint of its breath. For now, the numbers are what they are: carbon dioxide, dominant and persistent, outshining water in ways that make 3I Atlas unique. Scientists debate models, revise formation scenarios, and test alternative explanations. Yet, beyond the debates, the ratios linger in the imagination. Are they coincidence or choreography, a frozen accident or a deliberate code? The beauty of astronomy is that both answers inspire wonder. If natural, 3I Atlas shows us that alien star systems build comets differently, expanding our understanding of the galaxy's diversity. If intentional, then it is more than a comet. It is a message carried across light years, written not in letters but in chemistry. Either way, it reminds us that the cosmos speaks in many languages. The challenge is to know when it is whispering to us. When a comet streaks across our skies, we think of it as a singular event, a one-time spectacle. But what if each visitor were more than just a fragment of rock and ice? What if they were data points, a way to count how many civilizations might be out there? The idea comes from statistics. In astronomy, we often study populations indirectly. We cannot see every star in the galaxy, but by studying a sample, we can estimate how many exist. We cannot measure every asteroid, but by tracking a handful, we can model the distribution of sizes and orbits. In the same way, interstellar visitors like Oumuamua, Borisov, and 3I Atlas could serve as samples not just of cosmic debris, but perhaps of something more deliberate. If each visitor were purely natural, they already tell us something profound. Their numbers suggest that planetary systems eject vast amounts of material into the galaxy. Every star may contribute billions of fragments, drifting endlessly between suns. Detecting just 3 in less than a decade implies a staggering population of wanderers. Some estimates suggest there could be trillions of such bodies passing silently through the Milky Way at any given time. Each one is a messenger, carrying the chemistry of its birthplace. Each one is a chance to read the history of worlds we will never see directly. But if even one of these visitors were artificial, the implications would multiply. Suppose Oumuamua was a probe. Suppose 3I Atlas, with its strange chemistry and radar glints, is another. Then each detection becomes not just a comet, but a census marker. We would no longer be counting rocks. We would be counting civilizations. How might such a census work? Imagine a galaxy where advanced species seed probes disguised as comets. Each civilization might launch thousands or millions over the course of its history. They drift for millennia, blending with natural debris, passing unnoticed until they reach systems capable of studying them. If we detect 3 in less than 10 years, what does that imply? Perhaps there are hundreds more just beyond our reach. Perhaps their density is not random at all, but tailored to ensure that any emerging intelligence will encounter them. Of course, the skeptical view is more grounded. Oumuamua and Borisov were natural, and Atlas most likely is too. Their frequency is explained not by alien intent, but by better telescopes. Surveys are now sensitive enough to notice faint interstellar interlopers, whereas in the past, they would have slipped by unseen. If this is true, then the census we are taking is not of civilizations, but of planetary birthplaces. Even that is extraordinary. Each interstellar comet offers us a chance to sample the chemistry of another solar system without ever leaving home. It is like collecting postcards from distant worlds, carried across the galaxy on icy envelopes of dust. Still, the other possibility lingers. What if the true census is hidden within the natural one? What if some small fraction of these visitors are probes, and our job is to separate signal from noise? Just as the Drake equation tries to estimate the number of civilizations by multiplying probabilities, perhaps the appearance of interstellar visitors is another term in the equation. If they are natural, we learn about planets. If some are artificial, we learn about their makers. Either way, each detection brings us closer to understanding our place in the galaxy. So, when 3I Atlas passes and fades into the night, it may be more than a comet. It may be one entry in a cosmic ledger, a mark in a census far greater than any we have taken before. Whether it counts stars, planets, or civilizations, it reminds us that we are part of a story much larger than ourselves, a story measured not in decades, but in light years. Every object carries the memory of where it came from. For planets, that memory is written in rocks. For stars, it is encoded in their spectra. And for interstellar visitors like 3I Atlas, the story lies in both chemistry and motion. Its speed, its trajectory, its unusual carbon dioxide signature, all these clues point toward a possible birthplace, far older and stranger than our own, the thick disk of the Milky Way. The Milky Way is not a flat, uniform disk. Instead, it has layers. The thin disk, where our sun resides, is a relatively young, orderly plane of stars. These stars orbit calmly, with metallicities enriched by billions of years of stellar births and deaths. But above and below the thin disk lies another structure, the thick disk. Its stars are older, poorer in heavy elements, and move in orbits that are tilted and chaotic compared to ours. The thick disk is a fossil of the galaxy's past, formed during violent mergers and collisions billions of years ago. If 3I Atlas truly hails from this region, then it is not just an interstellar visitor. It is a messenger from a time long before the Earth was born. Its chemistry reflects conditions different from our solar nursery. Its speed, greater than any recorded interstellar visitor so far, may be the result of ancient gravitational encounters flung into space when the galaxy was still young. To study 3I Atlas is to glimpse the archaeology of the Milky Way itself. But what does it mean for us if this is true? If Atlas originated in the thick disk, then it has traveled for billions of years through the interstellar medium, surviving radiation, collisions with dust, and the endless emptiness of galactic night. It is a survivor, older than our solar system, older than the continents beneath our feet. Its ices are frozen time capsules of a chemistry forged in an epoch when heavy elements were rare, when the galaxy's stars burned with a different light. There is also a more speculative possibility. If civilizations arise not only in the thin disk, but in the thick disk as well, they would be unimaginably old compared to us. Their stars are ancient. Their worlds may have been habitable long before Earth cooled. In such a scenario, visitors like 3I Atlas may not be accidental debris at all, but deliberate probes launched in ages we cannot fathom. For a culture billions of years older, a comet-shaped probe drifting across the galaxy is not just plausible, it is patient strategy. Skeptics caution against this line of thought. The chemistry of 3I Atlas can still be explained without invoking intention. Its trajectory matches the expected distribution of objects ejected from star systems. The thick disk origin, while intriguing, is still a model, not a certainty. But even within the natural explanation lies wonder. To think that we are watching an object born in a galactic epoch before the sun existed is extraordinary enough. It means that when we study its coma and tail, we are studying a piece of the galaxy's deep memory. Whether natural or intentional, the thick disk connection deepens the mystery of 3I Atlas. If natural, it tells us that the galaxy is teeming with debris older than our world, drifting silently until chance delivers them to our skies. If intentional, it suggests that civilizations much older than ours may already have seeded the Milky Way with watchers, probes, or messages disguised as relics of creation. Either way, the conclusion is humbling. 3I Atlas is not just a visitor from another star. It may be a visitor from another age. Billions of years have carried it across the galaxy, and now, for the briefest of moments, it passes through our neighborhood. Like a ghost from the deep past, it reminds us how young we are and how ancient the universe's story truly island. Every object in the galaxy is on a journey. Stars orbit the Milky Way's center, planets orbit stars, and comets orbit suns until, sometimes, they are thrown free. Once ejected, these fragments wander the interstellar void, following only the invisible curves of gravity. To an astronomer, this is natural drift, motion without intention, shaped solely by physics. But with 3I Atlas, the question grows harder to dismiss. Its path through our solar system feels unnervingly precise, hyperbolic, yes, unbound, destined to leave forever. Yet it threads between planetary orbits in ways that seem almost choreographed. It passes close enough to Mars to invite cameras, close enough to the Sun to flare dramatically, and emerges again, just where Earth's telescopes can pick it up once more. For scientists, this is geometry. For others, it looks like navigation. Natural drift is messy. When objects are flung from their home systems, their trajectories depend on chaotic encounters with giant planets, stars, or even passing molecular clouds. Over billions of years, these wanderers should be scattered in all directions, moving with speeds and inclinations that feel random. To a degree, this is what we see. Oumuamua, Borisov, and now Atlas all arrived from different directions, each with unique properties. Yet, taken together, they suggest something odd. We are encountering these visitors more often than models predicted. Perhaps our surveys have improved, or perhaps something more deliberate is at play. To imagine intention is to step into unsettling territory. Navigation, in the interstellar sense, requires extraordinary capability. Even the smallest course correction, a few meters per second, applied over centuries, could steer an object toward specific targets light years away. To us, this feels impossible. But to a civilization millions of years older, Nudging a disguised probe across the galaxy might be no more difficult than steering a ship across an ocean. Some researchers have wondered if 3I Atlas's smooth, non-gravitational accelerations could be evidence of such control. Outgassing is the standard explanation. Sublimating ices, pushing it along like natural thrusters. But what if those thrusts are managed, regulated, guiding it not randomly but purposefully? What if the so-called drift is in fact a chosen path? The very ambiguity is the heart of the mystery. To us, outgassing and propulsion look nearly the same. Both create small nudges, both alter orbits, both leave signatures difficult to distinguish across millions of kilometers. Without a close-up view, we may never know whether we are watching nature at work or something more intentional. Of course, the cautious explanation is still drift. Interstellar space is vast, and given enough time, debris from distant stars will inevitably pass through our neighborhood. The fact that Atlas happens to do so in a way that feels convenient may be coincidence. Astronomers remind us that the solar system is not special, just part of the galactic flow. To ascribe purpose to its path risks repeating old mistakes, seeing intention where none exists. Yet speculation lingers, because navigation offers a profound alternative view of the cosmos. If 3I Atlas is following a chosen path, then we are not alone in drifting aimlessly. Somewhere out there, intelligence is steering quietly, subtly, perhaps watching us from behind the mask of a comet. For now, the evidence is not enough to decide. Drift or path, chaos or choreography, 3I Atlas remains a mystery. But the question it raises is timeless. Are we alone among wanderers, or is someone else out there guiding their course through the same galaxy we call home? Space is harsh. Radiation, collisions, tidal forces, and the relentless drag of time slowly destroy everything that drifts in the galaxy. For large bodies, planets, moons, and stars, gravity offers protection, holding them together across billions of years. But for small objects like comets, the odds are stacked against survival. And yet, here is 3I Atlas, a visitor from the deep past, intact enough to be seen, studied, and debated. Its very existence is a puzzle. Why should this surprise us? Because fragile bodies are not supposed to last. A comet is little more than a mixture of ice and dust, loosely bound. Sunlight erodes its surface each time it swings close to a star. Cosmic rays darken its skin, baking volatile ices away. Collisions with micrometeoroids chip at it grain by grain. Over millions of years, most comets either fragment into streams of debris or vanish altogether. Their gases gone, their nuclei reduced to inert rocks, indistinguishable from asteroids. Now, imagine the scale of interstellar time. If 3I Atlas was ejected from its parent system billions of years ago, how has it not already dissolved into dust? How has it survived radiation, shocks, and collisions over such immense spans? For an object thought to be fragile, its endurance feels improbable. Scientists have proposed explanations. Perhaps its nucleus is larger than it appears, giving it a sturdier reservoir of material. Perhaps its dust mantle is thicker, insulating the core and slowing its decay. Or perhaps, once it left its parent star, the cold of interstellar space preserved it like a deep freeze, locking its ices away until a new sun hours awakened them again. Each of these ideas is plausible. Each stretches our models of cometary survival. But some ask a different question. What if survivability is not an accident? What if 3I Atlas was built to last? The thought is unsettling but not illogical. If a civilization wanted to send probes across the galaxy, durability would be essential. Ordinary comets may erode too quickly to endure journeys spanning billions of years. But a modified one, reinforced, shielded, or engineered to mimic natural structure, could persist long enough to serve as a messenger. To us, it would appear improbable but still within the realm of possibility. To them, it would be deliberate design. Even if natural, the survival of 3I Atlas changes our view of the galaxy. It suggests that interstellar space may be filled with more of these wanderers than we once thought, and that their lifetimes are longer than models predict. This means that each star system seeds the Milky Way not just with debris, but with ambassadors of chemistry, drifting for eons until chance delivers them to another Sunday. Each survivor is a letter in a galactic archive, waiting to be read. Still, the mystery remains. Comets are fragile, and yet 3I Atlas has endured. Is it luck? Is it physics we do not yet understand? Or is it something else, something that pushes us to consider intention where we expect chaos? For now, the safest answer is preservation by cold. The interstellar medium is nearly absolute zero, and in such deep freeze, even fragile structures can survive for astonishing spans. But the image lingers. A comet-like body, carrying its chemistry through billions of years, arriving at just the right moment to catch our attention. Survivability, then, is more than a technical puzzle. It is a reminder that the universe is old, and that endurance itself can be a kind of message. Whether natural survivor or deliberate messenger, 3I Atlas whispers the same truth. Some things last long enough to be seen, even when by all rights they should have disappeared into the dark. In science, timing is often dismissed as coincidence. A meteor shower coincides with a historical event. A supernova erupts just as a new telescope comes online. We chalk these overlaps up to chance, not choreography. Yet, with 3I Atlas, the timing has raised more than a few eyebrows. Its closest approach does not align with Earth, as one might expect for maximum visibility, but with Mars. On October 3rd, 2025, 3I Atlas will pass within 29 million kilometers of the red planet, closer than many of its artificial satellites and orbiters. For planetary scientists, this is a gift. The fleet of spacecraft circling Mars from NASA's MAVEN to ESA's Trace Gas Orbiter, from India's Mangalyaan to the Chinese Tianwen probe, will have front-row seats. Their instruments, designed to study Mars's thin atmosphere, can be redirected to catch glimpses of a comet from another star. The chance is extraordinary, and it feels almost arranged. Why Mars? Why now? Natural explanations are straightforward. Orbits are orbits, and Atlas follows the same gravitational rules as everything else. Its approach geometry is the product of chance encounters long ago, nudged into this trajectory by forces we can only model in broad strokes. That it happens to pass Mars closely is coincidence, nothing more. If anything, it is Earth's luck that one of our robotic outposts happens to be there at this precise moment in time. But speculation invites another possibility. What if the timing itself is the message? Mars is the planet we have studied most intensely after Earth. It is covered in cameras, spectrometers, radar instruments, and antennas. It is our second set of eyes in the solar system. If an interstellar probe wanted to guarantee observation, Mars is the logical choice. Earth rotates, clouds obscure, daylight interferes. Mars offers constant orbital coverage, a near-permanent audience of machines waiting to measure. It is tempting, then, to imagine 3I Atlas's trajectory as encoded timing. An arrival calibrated not just for visibility, but for notice. By passing near Mars when it is heavily surveilled, the visitor ensures we will collect data, whether we mean to or not. The encounter becomes an experiment, not of its making, but of ours. This interpretation resonates with a long-standing idea in SETI, known as the synchronicity problem. If civilizations want to communicate, how do they coordinate across light years and epochs? One answer is to use natural events, eclipses, supernovae, or planetary alignments as meeting points. Anyone watching would know when to look. Arrival at a moment of maximum observation is not random. It is efficient. Skeptics rightly caution that this thinking risks anthropocentrism. Mars matters to us because we have put machines there, but why would it matter to anyone else? From the outside, Earth itself is far brighter, far noisier in radio, far more obviously inhabited. If there were intent, wouldn't an Earth flyby make more sense? And yet, perhaps that is exactly why Mars is ideal. A direct Earth encounter could provoke fear, panic, or hostility. Mars, by contrast, is neutral ground close enough for us to notice, distant enough to feel safe. A quiet stage where a visitor can perform without crossing our doorstep. For now, 3I Atlas is simply following its course. Scientists will analyze every spectrogram and light curve, searching for anomalies, while skeptics remind us of coincidence. But the timing will linger in the imagination. Not just a comet passing near a planet, but a visitor arriving when our cameras were ready, as if to say, "We knew you would be watching." For more than 60 years, humanity has wrestled with a quiet question. Should we merely listen for signals from the stars, or should we also speak? This is the core of SETI's dilemma, the search for extraterrestrial intelligence. On one side lies patience, waiting for whispers in the cosmic static. On the other lies boldness, sending messages into the void and declaring our presence. Listening has always felt safer. Pointing radio telescopes at the sky carries little risk. We record, analyze, and search for patterns. The danger is only disappointment, the endless silence of a universe too vast for our instruments. For decades, SETI has operated in this mode, scanning the hydrogen line, mapping frequencies, chasing fleeting anomalies like the wow signal. Each detection is checked, cross-checked, and usually dismissed as interference. The work is slow, meticulous, and humble. Messaging, however, is another matter. To transmit is to announce ourselves, to say, "We are here. This is our address. This is what we know." The 1974 Arecibo message was a symbolic gesture, powerful but brief, aimed at a star cluster so far away that no reply could return in human history. Since then, only a handful of deliberate transmissions have been attempted. Each has stirred debate, not about the science, but about the wisdom. Should we be telling the universe we exist without knowing who might be listening? This dilemma gains new weight when interstellar objects like 3I Atlas arrive. If they are purely natural, they remind us that the galaxy is rich in messengers of chemistry, offering us glimpses of other star systems without risk. But if even one of them is more than natural, if it carries intention, or if it is a probe disguised as a comet, then the conversation is already underway, whether we chose it or not. Listening, in that case, might no longer be enough. If we are being observed, silently studied by watchers hidden in cometary masks, should we remain passive, or should we answer? The decision is no longer abstract. It becomes immediate, even urgent. There are strong arguments for restraint. Civilizations capable of sending probes across interstellar space would be vastly older and more advanced than us. To reveal ourselves more boldly could be reckless, like shouting into a dark forest without knowing what predators roam there. Stephen Hawking once warned that any encounter with a far older intelligence might not end well for us. From this perspective, listening is the wiser path. Silence is safety. And yet, there are arguments for messaging too. Silence may not protect us. Our radio bubble has already spread 100 light-years. Our planetary radar beams, our television broadcasts, even our military communications, all have leaked into the void. To imagine we are still hidden is naive. In that case, deliberate messaging is not a new risk, but an honest acknowledgement of what has already happened. It is better, some argue, to control the story than to pretend we are invisible. 3I Atlas sharpens the debate. If its timing, chemistry, or radio whispers are more than coincidence, then perhaps the galaxy has already noticed us. Perhaps SETI's dilemma is no longer whether to listen or to message, but how to respond to what may already be a quiet dialogue. Do we continue to wait, pretending to be neutral observers? Or do we step forward, acknowledging that we are participants in a conversation older and larger than ourselves? For now, SETI remains cautious. We listen more than we speak. But the presence of interstellar visitors tempts us to wonder whether the time for patience has passed. In the silence of the sky, the question lingers. Are we hiding, or are we simply refusing to admit that the conversation has already begun? When most people think of the search for extraterrestrial intelligence, they imagine us listening. Dishes pointed skyward, headphones pressed to the void, waiting for a signal. But there is another side to the effort, quieter and more controversial. It is called active SETI, or METI, messaging to extraterrestrial intelligence. Instead of listening, it speaks. Instead of hiding, it announces. And in recent decades, humanity has done far more of this than most realize. The first deliberate broadcast was the 1974 Arecibo message, a 3-minute burst toward M13. But others followed. In 1999 and 2003, a series of cosmic calls were sent from the Evpatoria telescope in Ukraine, beamed at nearby stars. In 2008, NASA transmitted a song, The Beatles Across the Universe, toward the Polaris system. In 2017, a group of scientists and artists sent another coded transmission to a star 12 light-years away, carrying images, sounds, and mathematical concepts. These were not accidents, they were invitations. And then there are the unintentional broadcasts. Decades of radio and television, radars so powerful they can light up a star system light-years away, pings from planetary defense systems, and the Deep Space Network's constant conversations with our spacecraft. Together, they form a messy, unplanned beacon. Whether or not we call it active SETI, Earth has been an active transmitter for a century. So when 3I Atlas entered our solar system in 2025, some asked the unsettling question: did we invite this? If Atlas is purely natural, then the timing is coincidence, the overlap with our transmissions nothing but chance. Billions of comets wander the galaxy. It was inevitable some would pass by. But if Atlas is more than natural, if it is a disguised probe, or if its chemistry or radio whispers are deliberate, then active SETI may have worked. Perhaps our signals, drifting outward for decades, were heard by someone close enough to respond within half a century. Perhaps what we see now is not coincidence, but reply. The thought is both thrilling and unnerving. On one hand, it suggests we are no longer alone, that we have succeeded in drawing the attention of another intelligence. On the other, it raises the oldest fear of all, that we called into the dark without knowing who might answer. Stephen Hawking once cautioned against active SETI, warning that advanced civilizations could treat us the way Europeans once treated less technologically advanced peoples on Earth. To send invitations without consensus, he argued, was reckless. But not everyone agrees. Advocates of active SETI argue that silence offers no protection. Our radio bubble has already spread 100 light-years. Any civilization within that sphere knows we are here. To pretend otherwise is naive. In that sense, deliberate messaging is not a new risk, but an extension of what we already do. If we are broadcasting anyway, better to craft intentional messages than to let sitcoms and radar pings speak for us. 3I Atlas places this debate in a sharper light. If it is natural, then active SETI remains a theoretical gamble, a question for future generations. But if it is artificial, even partially, then the gamble may already have been played. Our invitations may have been heard, and the guest has already arrived. Of course, science demands caution. There is no proof that Atlas is anything but a comet. Its anomalies may all have natural explanations. But the coincidence is haunting. Messages sent, a century of noise. And now, a visitor perfectly timed, perfectly placed, just as our technology becomes capable of noticing. Whether or not we invited this, the question will not go away. By transmitting, deliberately or accidentally, we have entered into the conversation. The only uncertainty is whether 3i Atlas is coincidence or whether it is the first whisper of a reply. There is a middle ground between a single stranded probe and a planet-spanning invasion. The probe swarm. Imagine not one metallic craft crossing the gulf between stars, but thousands or millions of tiny devices traveling together, dispersed like seeds on the wind. Each individual piece is small, almost trivial. Together they form a resilient network. Redundancy, coverage, and a distributed intelligence that no lone ship could match. When we look at 3i Atlas, that image is worth considering. Why a swarm? The virtues are practical. A single large probe is vulnerable. One catastrophic collision, one failure of guidance, and the mission could end. A swarm, by contrast, trades size for numbers. It tolerates attrition. If some members vaporize from interstellar dust or are shattered by micrometeoroids, enough survive to continue the task. A distributed array can sample widely, triangulate sources, and act locally. One element photographs an atmosphere, another samples a coma, a third performs radio monitoring. For an intelligence that can plan on million-year timescales, sending a swarm is efficient and robust. How would a swarm hide? Nature provides excellent cover. Small devices encased in ice, cloaked in dust, or embedded in rocky fragments would appear cometary to telescopes. A swarm can deliberately vary apparent sizes and behaviors to mimic natural fragmentation. A mother nucleus that sheds many smaller fragments, each behaving like a microcomet. From afar, such an ensemble would look familiar, a cloud of outgassing bodies while containing within it instruments and reflective surfaces that betray occasional, subtle anomalies. Mirror-bright glints, oddly coordinated light curves, or correlated non-gravitational nudges across multiple fragments. Technically, formation flying across interstellar distances is challenging, but not inconceivable. Propulsion could be light pressure on ultralight sails, small nuclear or fusion microthrusters, or even staged gravitational assists. Communication within the swarm could be local and low-power optical flashes, magnetic coupling, or passive backscatter, minimizing signatures that would otherwise flag them as loud artificial transmitters. The swarm could remain largely silent until it reaches a target system, then opportunistically wake sensors when a star warms their icy shells. The result? The first impressions to outside observers read as cometary behavior, while the swarm quietly collects data. What observational signatures might betray a swarm? There are a few possibilities that astronomers would look for. One is coordinated behavior among multiple fragments. If separate pieces of the same visitor show correlated accelerations or synchronized brightness modulations, that points to control rather than chance. Another is anomalously persistent reflectivity in certain wavelengths, sharp spectral peaks, or polarization signatures, inconsistent with typical cometary dust. A third clue would be oddly precise timing. Fragments whose light curves or radio emissions encode regular patterns, primes, mathematical ratios, rather than chaotic outgassing noise. Even small, temporary radar specularities, mirror-like returns at predictable rotation phases, would raise eyebrows. Yet, there are counter-arguments. Sending a swarm imposes mass and energy costs. Dispersing many units increases the logistical burden of acceleration, guidance, and longevity. Self-replicating probes solve some of this, but introduce new complications and ethical questions. Additionally, nature can and does produce ensembles of fragments, tidal disruption, rotational breakup, collisional cascades. Distinguishing between natural fragmentation and an engineered swarm requires robust, repeatable anomalies, not single oddities. Finally, consider motive. What would motivate a civilization to deploy a swarm disguised as comets? Surveillance is one answer. A long-term, low-risk observation program to watch emerging technosignatures without interfering. Another is sampling. A distributed fleet can collect material from diverse systems, building a library of planetary chemistries. Or perhaps it is a cultural decision. Leave many small relics across the galaxy as archives, patient and silent, waiting for budding civilizations to mature. In the end, the swarm hypothesis is seductive because it sits between the mundane and the miraculous. It explains survivability, stealth, and redundancy while remaining technically plausible for a very patient maker. But it also demands evidence, patterns that cannot be reduced to geology, chemistry, or chance. For now, 3i Atlas offers hints, glints, chemistry, and timing that provoke questions but no conclusive proof. The idea of a probe swarm invites us to listen more carefully, to look for coordination where we once assumed randomness, and to accept that intelligence might choose subtlety over spectacle when it first comes calling. When sailors once crossed the Earth's oceans, they depended on lighthouses. A tower on a rocky coast, burning a steady flame, offered guidance and warning. The point was not to start a conversation. It was to be seen. To declare, here is land, here is danger, here is civilization. On a galactic scale, some scientists have wondered if the same logic might apply. Could advanced civilizations build interstellar lighthouses, beacons designed not to talk, but simply to be noticed? In many ways, the physics make sense. The galaxy is vast. Distances between stars are measured in light years, journeys that could take millennia. Direct contact may be impractical, but a beacon, steady, obvious, unmistakable, sidesteps the problem. It does not require a reply. It only requires recognition. Someone is here, it says. This is not an empty sky. The idea has deep roots in SETI. As early as the 1960s, astronomers like Cocconi, Morrison, and Drake proposed that if aliens wanted to signal, they would choose frequencies that all civilizations would naturally study the hydrogen line at 1,420 MHz, or its harmonics. These would act as cosmic signposts, universal channels where anyone with radio telescopes would eventually listen. In fact, narrowband signals at exactly these frequencies have long been prime targets for SETI searches. The WOW signal of 1977 was intriguing precisely because it matched this expectation, a sharp, unambiguous spike in hydrogen's neighborhood. But what if beacons are not only electromagnetic? What if they are physical? Interstellar objects like Oumuamua, Borisov, and now 3i Atlas invite this speculation. Instead of building transmitters that must run endlessly, a civilization could launch physical markers, comets modified to carry signatures, probes designed to mimic natural debris. These would not converse but would appear. Their very arrival would serve as a lighthouse flash, rare, brilliant, impossible to miss for any civilization watching the skies. The logic is simple. Energy is expensive. Broadcasting across the galaxy continuously might be wasteful or unsustainable. A single probe or altered comet, by contrast, can endure for billions of years, drifting silently until it is seen. It requires no constant fuel, no constant maintenance. It works on cosmic timescales, and if enough of these lighthouses are seeded, the chance of being noticed by emerging civilizations grows close to certainty. Critics argue that this idea is anthropocentric. Why would an alien civilization go to such lengths simply to be seen? Why not remain silent? Why not focus on survival rather than spectacle? Yet history offers parallels. Humans have built monuments, from pyramids to radio towers, that outlast their original purposes. Some are practical, some symbolic. A galactic lighthouse may serve the same dual role, partly functional, partly cultural, an act of presence as much as communication. So where does 3i Atlas fit into this story? Its timing, its strange chemistry, its radar glints, and its whispers near the hydrogen line make it feel like more than chance. If it is a beacon, then its job is not to speak in sentences but to shine, briefly and unmistakably, as it passes. The message is not content, but context. You are not alone, and this sky contains more than rocks. For now, we tread carefully. Astronomy teaches humility, reminding us that nature often surprises us with patterns that imitate intention. Yet the lighthouse logic lingers because it is efficient, elegant, and universal. To build a beacon is to understand that across light years, words may fail. But presence endures. Perhaps, then, 3i Atlas is a natural relic, a chemical postcard from a star system long gone. Or perhaps it is something more. One of countless lighthouses scattered through the galaxy, waiting patiently for young civilizations like ours to notice the flash in the dark and realize we are not sailing alone. So, is 3i Atlas alien? The honest answer is no one knows. The evidence we have points toward natural explanations. Its chemistry is strange, but not impossible. Its path is hyperbolic, but predictable. And yet, in the gaps of our certainty, imagination finds room to grow. Perhaps that's the real gift of 3i Atlas, not proof of aliens, but a reminder that the universe is still capable of surprising us, humbling us, and asking us to dream bigger. As the comet fades into the dark, the question it leaves behind lingers. What if we are not alone?